We've gone through the electric field formulation from a single charge to a differential charge, and then we went ahead and integrated the charge density either over a line or a surface, or we could theoretically do it over a volume, but we have obtained the electric fields for a lot of canonical shapes: infinite surfaces, infinite lines, and point charges. Now what we're going to do is talk about Gauss's law. How many have heard of Gauss? He is my hero. Anyway, Gauss's law is very powerful for one reason. If there's a high level of symmetry, you can easily obtain the value of the D field, and from that get the value of the E field. Y'all hear me on that? So it's for problems with high levels of symmetry. Actually, Gauss's law says this. It's just this, that the integral, and this is the integral formula, over a closed surface of the D field dot ds is equal to the charge enclosed. Now, that's called the integral form. It doesn't mean much to you in itself. But it says that you can find the D field, you got it into a surface that completely encases the charge. It has to be a closed surface. Then it will be equal to the charge inside the surface, and you'll see how this applies. This is called the integral form of Gauss's law. The differential form is divergence of D is equal to rho V. This is very, very important as well. I'm going to say one thing here also to try to put everything in perspective. D and E, the D field and the electric field are related by epsilon E. Now, epsilon is the permittivity of the material or region. Epsilon generally is equal to epsilon relative times epsilon naught. Epsilon naught is what we've used so far for a free space. And it's really in a vacuum what the value of epsilon be. Epsilon naught, now Dr. Whitworth spoke, he likes to put 1 over 36 pi times 10 to the minus 9 farads per meter. And I noticed grading the quiz, a lot of people use that. That's fine. Right. It's approximated a lot of times as this. About 8.854 times 10 to the minus 12 farads per meter. These two will be close, but they won't be the same. Y'all, yes, sir?
Is the 36 pi exactly right? Or is that just...
This is a discussion. Okay, so long ago when they did measurements of all the things that they could measure, they measured the H field, the E field, and all that stuff. And they came up with two laws. There was curl of H is J, basically that's the differential form, and that's assuming that there's no time-varying electric fields. And the second was curl of E was minus dB dt. That's Michael Faraday's law of induction. Now, when they did this, the first sets of equations were written in English units, not in MKS. This is what we use. So the pi started to appear when they're, what exactly is the speed of light to you? Well, the speed of light is equal to 1 over the square root of mu naught epsilon naught, and that's in a vacuum, right? So what's mu naught? Does anybody remember this? It's 4 pi times 10 to the minus 7 henries per meter. What's epsilon naught? Well, if you want to use 1 over 36 pi times 10 to the minus 9, and you go there, you're going to see the pi's cancel, and you get a nice number there. And it comes out to be 3 times 10 to the 8th meters per second. Is that the speed of light actually in a vacuum? It's about 2.99, all that crap, right? All right, so it's not exact, but it is more precise than some of the other prior estimates. I'm just telling you that. What else?
Okay, so the pi's don't actually exist, but the pi's describe a relation
Pi is what?
between the...
No, wait. Before you go too far down that path, I'm going to cut you off in a second. What is pi? How did it come about? Anybody? Remember back in the day when they took the perimeter of a circle, right? Back in the day of the Greeks, right? What did you know about that? 2 pi times the radius was the circumference, right? That's how that number was created. It's a never-ending, what do they call that thing? It's not repeating, it's a never-ending...
Irrational.
Yeah, but there's a there's another term for it. It's a rational number, but the thing, like 3.141, blah, 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 and it goes on forever. It's not a closed form. So that's where pi comes from. Let's not do this today. Anyway, this sounds like a Friday afternoon happy hour discussion. Anyway, back to this. And, well, actually this is the form. Now, I want to add one more thing about this. Remember, because of this, write this down. This is important. The divergence of E, if you just replace D by epsilon E, you can see divergence of E is actually the rho V over epsilon. And I leave it as epsilon. It's usually epsilon naught unless otherwise stated if it's a material. So that's basically the forms of Gauss's law. Now I'm going to show you how come it's so powerful and useful to us. And let me just say one other thing too. If you ever are curious about this, look up the life of Gauss, look up the life of Sir Isaac Newton, look up the life of de Broglie and some of the other, before you get into modern physics with Einstein and stuff like this, go back to the classics. Look at actually go ahead and look at Michael Faraday, Ampere, and then James Clerk Maxwell that put it all together. These are amazing, clever individuals that came up with unbelievable insight into mathematical ways of describing the universe. They didn't have a lot to work for, or a lot to work with back in the day. Okay, so here's Gauss's law in a nutshell. Here's why it's so powerful. I'm going to start with the simplest possible example that you know the answer. Suppose I have just a charge, Q, and it's located at the origin. Everything else doesn't matter. Now, a natural surface around there would be a spherical surface because if it's concentric with this, the radius from this point to the sphere of the surface would be the same everywhere. Y'all follow me on that? This is important. Y'all see how that's symmetric, I just said. Now I make the assumption, and it's true, that the D field, this is a charge, the D field will be radially outward everywhere. So it's going to point outward. Can everybody follow me on that? Now I can formulate an integration and do it for a differential surface vector and do the whole thing, but I'll show you how this thing unfolds with Gauss's law. Gauss's law says the integral of d dot ds over any closed surface is the charge enclosed by that surface. Everybody follow me? Well, the charge is Q. That's a no-brainer. I created it. That's how much charge is in there. Everybody follow me? So I just put Q over here. Now, the surface vector D, this is where you have to have some insight. Do you see how that's always going to be pointing? If you know anything about electric fields and about D fields, they always point radially away from the charge center. You all follow me? If it was negative, it would be pointing that. That means if I look at this, and then I take a look at a differential surface vector here, you don't need to write this down. The differential surface vector will have a surface, an area, and if it's spherical coordinates, it's going to be r squared sine of theta d phi. R is going to be held constant. It will be in the AR direction. So if I look at that, just for a second, and I dot it into my D field, I know D field is only going to be in the AR direction, and the magnitude would only be a function of the radial distance away from the center of the charge. Y'all follow me on this, class? I'm spending a lot of time saying stuff that's pretty obvious to everybody. So I could do this integral. I could put this right here as ds, and that would be a double integral over theta and phi, and I could do it. At the end of the day, it comes down to the surface area of a sphere times the D field. Y'all hear me? What's the surface area of a sphere? Surface area is 4 pi r squared, where r would be the radius. How many know that? Right. Please make sure you know that. What's the volume of a sphere? 4/3 pi r cubed, right? Volume is cubic, surface area squared. Do you all agree with this, class? So the surface area down here would just be 4 pi r squared, and then it's going to be times dr, and that's equal to the charge enclosed, right? So what is the D field going to be? Well, it's pretty obvious. The D field from a point charge is going to be Q over 4 pi r squared in the AR direction. Now, You already knew what the E field was from a point charge, right? But if we have a D field and we want the E field, what do? Take a look over there. Guys, divide by, well, can you read? My writing's bad, but it's not that. Can you all read it? If we have B and we want E, what do? Divide by epsilon, right? The permittivity, that's it. So if we wanted the E field, that's the E field. Now, just showing the relationship. Now I'm going to do the next they call them canonical shapes. That's going to be a line charge. Do you already know the electric field form from a line charge? Yes, but I'm going to prove it to you with Gauss's law. You'll see how this works in a second. With some of the things that aren't so, that we would not want to do a differential. The way we did it in the past was we had a differential amount of charge. We found the differential electric field from that differential charge. Then we integrated over wherever the charge exists to get the total electric field, right? Integrations can be lengthy, time-consuming, and irritating. This method, if you can find symmetry, is easy. It's a no-brainer, as they say. I wonder where that term no-brainer came from. All right, so now remember, the shapes have to be symmetric, or they have to work conformally with the surface or the line or the point you're talking about. So if I have an infinite line charge here, we're going to assume this has a line charge of rho L, okay? We're going to assume it's constant, but it's infinitely long. Now we're going to put a canonical shaper in there. Please watch this part. So here, I'm going to put a cylinder. Now, does everybody see how that cylindrical surface is conformal with the line? If you collapse the radial distance, it would become the line. You all follow me on this, class? It works. There's more ways to explain this mathematically, but the surface has to be conformal, and it should look something like this. So I'm going to say this has a radius rho. I call this the z-axis. It doesn't matter. Now, here you have some liberty. You can make the height of that cylinder anything. Whenever you're given a choice to make something a given height, and it can be anything, make it 1. Make it 1. You can't mess up. All right? So I'm going to assume the height is 1. All right. Now, that's an infinite line charge based on your understanding of field theory, electromagnetism. You realize the electric field and the D field, since they're one and the same in terms of direction, are pointing away from that line charge. Do you all agree with that? So I'm going to say that the D field is going to be radially outward on this surface. Okay? You all follow me? And I'm just going to say that D field will have a form. It will vary with distance, but it will not vary with theta or z. You all follow me? It doesn't matter the angle, and it doesn't matter how high you are if it's infinitely long. So here I'm going to say the D field has some value, and it is only a function of the radial distance here, and it's going to be in the radial direction, so I'll call it A rho. Now when I look at this, Gauss's law says the integral of B dot ds over the closed surface is equal to the charge enclosed. You agree with this? So how much charge is in here? Well, the charge density is rho L. That's what? Coulombs per meter, correct? What's the height? How much? Rho L. You all right? In the meters we cancel. Just leave it as rho L. This is nice. Now, back to this integration, surface integration. Please watch this. I made a statement that the D field is radially outward. We could argue from symmetric aspects of this for every charge. Here you have an equal amount below it that would cancel the vertical component. You all follow me? Now, we can argue this like the D field's only in the radial direction. What happens when I do the integral of B dot ds over that surface? Well, what direction is the surface vector on the top part, anybody? Or bottom? Remember, differential surface has magnitude and direction. The direction is always perpendicular to the surface plane. You all follow me on this, guys? So it's in the AZ direction. Do you agree with that? How many see this right here? All right. If it's in the AZ direction here, That would be, the normal component would be AZ. Down here, it would be in the minus AZ. Do you agree with that, class, the surface vector? All right, when you dot AZ into A rho, what do you get? The dot product is what? It's like taking the cosine of the angle between the two vectors, right? What is the angle between these two vectors if I've got AZ and A rho? Class?
90.
90. What's the cosine of 90? 0. No.
Yeah.
Sine of the angle, isn't it? Sine of the angle. You were right, actually. I give yourself credit. I'm sorry. It's going to be the cosine of the angle, which is going to be of 90 is 0. Correct, class?
Mm-hmm.
It is 0. Do you all follow me on this, class? So here, there's no contribution here or here. It's only the outer surface, right? Now follow me on this. What's the outer surface of a cylinder? Well, it's the perimeter or circumference times the height, right? What's the perimeter? 2 pi rho, right? 2 pi the radial distance, which is rho. So when I look over here, I could do this integral. I may do it anyway, but I'm showing you the quick way. It's just going to be the perimeter, or 2 pi rho here. It's going to be magnitude d rho, because the A rho surface vectors in the radial direction dotted into the D field would give me a value of 1. Then it's going to be what? Times the height. What's the height? 1. Right? You all follow me? So I just took the area of that outer can times the D field, the value d of rho, set it equal to the charge inside right here. What do you see happening? D of rho becomes simply rho L, that's the charge density, over 2 pi rho. And it would be, if we wanted to make a formal D field, we'd just put this as A rho. Does everybody agree with that? I'm going to show hands if you see this. It may seem boring, but it's not. You're going to see the applications to some more difficult problems and how they make it so easy. Now, if I wanted the E field from that, what do? Let's assume it's free space. Anybody? Divide by epsilon. Correct, class? So if I wanted the E field, I would divide this by epsilon naught if it's free space, and then I get the E field. All right? That's the second one. Now, we can also do a plane. And this gets, my drawing may be a little weak here, but I'm trying to show you how they usually teach this in physics at the basic level. So this is the z-axis. Now I've got an infinite plane of charge in the xy plane. Call that x, call this y, and this is z equals 0. So right at the surface, the xy plane, I have some rho s that's a constant. And it's everywhere. You all follow me? By the way, that camera, this projector's on, I gotta show it. All right. So, if I try to apply Gauss's law here, you're going to see the only thing you have to do is capture something that has no variation in cross-section and height. It doesn't matter the shape. You can make it a cylinder, you can make it a cylindrical block, or a rectangular block, it doesn't matter. I'm going to make mine a cylinder. We call this a pillbox, usually. And I'm going to assume this little pillbox of mine, they call it a Gaussian surface. If I'm going to use Gauss's law to figure out something about like the D field, then I have to create a Gaussian surface, which is an imaginary construct. And I'm going to say, here's the plane, all right? Half of it's above, half of it's below. The height h can be anything, so I make it 1. You all with me on this? Might as well just make this have an area. It doesn't even matter the shape. I'm going to call the area equal to A on the top, and that would be pi times rho squared if this was the radial distance rho here. But it won't matter. Now if you look at that for a second, remember half of this thing is above, half of it below. It's a little cylinder. Think of a tuna can, all right? An empty tuna can as the Gaussian surface. It's centered so that the charge is right, that plane of charge is right in the center of it. Y'all follow me? Now, can you all see, based on arguments of symmetry and prior knowledge, we have an infinite plane. The E field or D field is either going to be up or down. No horizontal components. Can you all appreciate that? So you have to be able to see symmetry in a problem to use Gauss's law effectively for the integral form. So that means the total charge inside that region is equal to the integral of the d field on the top surface and bottom. Integrate. Y'all follow me? Now just watch this. So that means over here, and I'm being a little sloppy, but I think you'll see this. When I do the integral of d dot ds over that surface, the outer part is going to only contribute 0 because the d field is assumed to be in the z direction. Here, the surface vector would be in the horizontal plane. It would be a rho, basically. Can you all see that, class? Give me a show of hands if you can. That means when I take the dot product of the d field times that cylindrical surface, it's 0. So I don't worry about it. I just worry about the top and the bottom. Can you all follow me? Now, remember the d field above the plane is going to point upward, below the plane downward. Hear me on this? The differential surface on these things is always pointing away from the enclosure of the surface. So here the differential surface points up. And here the differential surface points down, or negative. Negative times the d field that's got a negative sense is a positive, right? So really when I do this integration, it's going to be 2 times the area, and I'll just call it 2 times a, times the value of the d field on either one, the top or bottom, the magnitude. So it's going to be the d field, and in this case it's in the z direction. That's equal to the charge enclosed, right? How much charge is inside here? Well, it would be the charge density times A. Do y'all follow me how that would be the charge? Can you all see this, guys? So that means it's just simply going to be equal to rho s times A. Now, at that point, and remember, I'm not trying to do this by doing all sorts of complicated integrals. It doesn't require it. Your understanding, this level of understanding is all you need to use this effectively. But now, when you do this, what can you see? The A's cancel, don't they? That area cancels. You all follow me on this, class? And you can see here, I have that. If I divide by 2, now I have the d field. I like to say it this way. This would be the A normal direction of the d field. Now, if I'm above the plane, it's that way. If I'm below the plane, it's that way. Can you all appreciate that? What do I do to get the E field from that? Just divide by epsilon. How many realize that is the E field from an infinite plane of charge? Right? Your last quiz, you had that on there. You're with me on this? And this is Gauss's law being used for problems that have a high degree of symmetry. Now we're going to do a problem that would be difficult with an integration form of the electric field D field, but trivial when it comes to using Gauss's law. And as you might have guessed, most of those are going to be cylinders. And he has some, so I'm going to do the classic one. There's a lot of others, but Gauss's law is something that I believe you've had Gauss's law in physics. Your teacher probably took some time and explained why, how valuable it was and why it was valuable. I can tell you that until you do a whole bunch of different types of problems, you don't appreciate it fully. You have an idea of what you can do with it, but you don't know what you're really doing. So now we're going to do this. Here's the z-axis, but now I'm going to put something that's going to be a bar, a solid. This is going to be an infinitely solid tube. It goes on to infinity. Call this the z-axis. And inside this radius A, I'm going to say I have a volume charge density of rho v. And outside A, I'm going to say the volume charge density is 0. So the tube's got a whole bunch of charge evenly dispersed in it. Follow me on this? That's the volume charge density. Sometimes in Whitmore's book, what he does is give you a total charge per length, and then you have to divide that by the volume to get rho v. Can you all follow me? Now here, we're going to have 2 regions, where Gauss's law will be a little different. We're going to have a region, just follow me this. By the way, what shape might I use for my Gaussian surface? Take a stab at it, anybody.
A cylinder.
Absolutely. Anytime you see anything like this, call it a fat wire. It's a cylinder, always. What's the height of the cylinder? If this is infinite, what's the height of my cylinder? Always 1. So this is going to be inside. So first I'm going to say, for a radial distance less than A, here's my Gaussian surface, and I'll try to draw it good. It's going to look like this. It's going to have a height h, which will be 1. This is my rule. Never make your life hard. It's hard enough without making it any harder. So always go for constants and values that are the easiest to work with. 1 is something I can deal with. All right, this has got a radius rho. You all follow me? This is inside where that charge density is. Now Gauss's law says the integral of d dot ds over the closed surface is the charge enclosed by the surface. Okay, that's what it says. So take a careful look at this and think about it. All right, that cylinder is something we just saw with the line charge, right? I have to make the assumption that the D field is radially outward. I have to, all right? And I can make arguments of symmetry, and Whitmer's book, he does this fairly well. He's more or less for every charge here, I have the same magnitude charge below a point at a given distance, which will cause the vertical fields to cancel, the horizontal fields would still remain. That's basically the premise. So if that's the case, when I look at this, remember this has a flat top here. The surface vector ds here is in the az direction. The surface vector here is in the minus az direction. Az dot d a rho is 0, correct class? So I don't worry about the top and bottom surface here. Only the outer surface and the d field value. You all follow? Now the d field will change with radial distance here. But this integration, and we could write it down formally and do it, it's just going to be the surface area, which is going to, what's the surface area? We just talked about it. It's 2 pi what? Rho, right? Now my rho is not A, it's inside there. And it's times d rho. All right, so that would be the d field integrated over the surface area. And it is a function of distance, and we'll see that, is the charge enclosed. Now how much charge is inside here? What do I need? I said rho v was a constant, didn't I? It didn't have to be a constant. If it wasn't a constant, I'd have to do a formal integral. But what is it really going to be? If it's a constant, it's rho v times the volume of that cylinder. Do you all agree with that? So what's the volume of a cylinder? Well, the height, what's the height? 1. And it's times the area. What's the area of a circle? Pi rho squared, right? It would be pi rho squared times the height, which is 1, times rho v, volume charge density. You all follow me on this, class? Now we can get, by the way, this is a pain in the butt problem if you're doing it differentially. If you're going to take a little differential amount of charge here, get the differential D field or E field at a given radial distance and do it for the entire integration, you get elliptic integrals. Trust me, you don't want to do them unless you have to. It becomes difficult, is what I'm trying to tell you. Do you remember, have you had elliptic integrals? No, you're not. No. All right. Well, when you get through them, you realize I hate them. That's my conclusions from that. And this is recorded.
I can pause it.
Well, let's just say that comment really doesn't apply to anybody else. All right. Over here, now what is V rho? Well, you all see the pi's cancel, class, right? And you can see rho will cancel rho squared, but it's still rho. You all follow me? So I've got rho over here. And then I have rho v, and it would be in the A rho direction. Now that would be the D field that you would get inside there. You all follow me? If I wanted the E field, what would I do? Simply divide by epsilon. Yep.
Is that over 2 as well?
Yes, it's over 2. That's my error, right? Okay, you're right. It's over. Now that's inside, right? Please watch this next part support. Now let's go outside. That's the D field. To get the E field, we divide by epsilon. Okay. Now we go outside this region. So now we're at a value of rho greater than A or equal to A. Gauss's law still applies. The integral d dot ds over closed surface is going to be the charge enclosed by the surface. But here, watch this. Now I'm going to go outside the region. I'm going to leave the height be 1. So now I'm going to have something like this. And I'm trying to draw this and superimpose this on this shape for a reason. Y'all see this, class? So now, this is my can right here. Okay. You can see that the D field's still radially away. So the integral of the D field dotted with the surface vector on the top is going to be 0 as before, and the bottom is 0, right? So really I need the D field just on the outer part, which is identical to what we just calculated. So what's that value going to be? Well, remember we did that here, right? It's going to be 2 pi rho. That's the circumference now of my, but rho's greater than a here. Y'all follow me? And then it's going to be times h. Isn't that the area, the outer area, class? Then it's times the D field. Well, h is 1. And that's the charge enclosed. How much charge is inside there? Here's where people make mistakes all the time. Well, we would have to go right to here, right? We'd have to go and say we can only calculate the amount of charge up to the radius a, because after that the charge density goes to 0. Does this make sense to everybody, class? How many see this right here? Charge density is rho v. Now we need the volume of that inner core, right? So it would be rho v. What's the volume of a cylinder? The height, which is 1 times what? The actual area, right, of the top or bottom part, right? Area would be pi a squared now. Now rho goes to a, right? So it would be pi a squared. And that would be the D field. We're going to calculate it. That would be beyond the range of rho equal a, the radial distance equal a. Everybody follow me on this, guys? So what's it going to be? The D field here is in the radial direction. I'll put a rho in a second. The pi's cancel. I get a 2 downstairs, and I get 1 over 2. And here you're going to have a squared here divided by rho times rho v in the a rho direction. Agreed, class? Now, you'll notice that that falls off as 1 over rho, doesn't it? It's identical to an infinite line charge. As a matter of fact, if you take all the charge here and collapse it down to a line charge instead of a volume charge, you will get exactly the same thing that you had before, which is just rho L over 2 pi rho and divided by epsilon for the E field. Y'all remember this, class? So if I wanted the E field, I divide this by epsilon, right? Then I get the E field. And it falls off as 1 over r. It varies as 1 over the radial distance. That's an important fact to know. How fast does the E field vary, static E field, from a point charge, class? It varies as 1 over r squared, right? It's 1 over r squared. Here it's 1 over the radial distance, single power, right? How does it vary from a plane of charge if it's infinite? It doesn't vary. It's constant, right? The E field from an infinite plane of charge or the D field would have a constant value in magnitude. It would change directions when you went below the plane. That's the only thing. All right, keep that in mind. Okay, so that's Gauss's law applied to 2 things, 3 things actually, and the problems in the book. I'm going to give you some problems, and they're really not going to be overwhelming. They're going to be fairly easy to do. But the big thing that I'm going to tell you with these problems is that you have to do them. You have to do them to appreciate how you do it. Now, read this section in the book. He talks a lot about this in on page 165. He's got some pictures on it, but Gauss's law in both the point form and the integral form are in his book. And if you look on, starting on page 153, you can read through it. Now, what I've just said is what he talks about, but I try to avoid it's very much applied. How would you do it if it was you doing the problem? You could write the formal integration. It's a waste of time in a sense if you already know the answer. You don't need to do it. All right. Now, I'm just going to talk for a second about the divergence form of the D field. And a couple things I'm thinking about. Let me just show you. This is the trivial thing. Now, you all have your books with you? If you go to the back cover of the book, you're going to see something where they show you the divergence operator. It's that upside down triangle with a dot, and then it's multiplying a vector, usually D. And it'll show you the form. So I'm going to just write this down for you. We'll do them. We'll do a few of them. So, remember, the differential form of Gauss's law is divergence of D is equal to rho V, the volume charge density. So, probably a good thing to take a look at is, suppose I give you a D field and I expect you to do this operation. Now, if you look in the back cover, you can go, I'm going to start with Cartesian. Suppose I said the D field itself is x squared y ax plus z squared y ay, and leave it at that. And that would be, the units of this are going to be coulombs per meter squared. Now I want to know what the charge density is anyway. So I have to do this divergence operator. You all see this, class? How many have your books? Well, not a lot, but enough of you. You can look on somebody. Divergence operated in Cartesian coordinates, it will always be a scalar, and it will be the derivative with respect to x of dx plus the derivative with respect to y of dy plus the derivative with respect to z of dz. This is in Cartesian. How many remember seeing that in your mathematics courses? I mean, I think they teach this, but when I ask people, sometimes they're looking at me like, never seen it. Okay, so what is this going to be? Just do the math on this one. dx is the coefficient of ax, right? What's the derivative of that with respect to x? Anybody? 2xy. 2xy, correct, class? So it's 2xy plus, now what's the derivative of dy with respect to y? Can you all see it's just z squared, right? It's plus z squared. And that would be rho v. There's nothing else, right? Now, let me ask you this. What would rho v be at the origin when x and y and z are 0? Just look at the equation. 0. Can everybody see it 0? All right? I'm trying to show you how simple it is. Now, I use Cartesian. If you use cylindrical coordinates, then you should have all these in this book. In cylindrical coordinates, what's the divergence? There's a couple different ways to write this, right? In cylindrical coordinates, it'll be what? I'm not sure if he does the 1 over rho form or if he does a couple different ways to write this. I'm going to take a look and see what form he has here. These aren't hard to do, by the way. So, oh yeah, he has the 1 over, okay. And so he's going to have 1 over rho d rho of rho times d rho. You can also go ahead and do this operation and separate it into two terms. That's the only reason I'm saying. Then it's going to be plus 1 over rho d phi of d phi plus the derivative of dz with respect to z. So let me make up a field. Suppose my d field is equal to, let's see, it's going to be 5 over rho a rho plus 6 times the sine of phi, a phi, plus 2z az. And this, of course, would be in coulombs per meter squared. Y'all follow me? I just created this. So let's go ahead and do it. Now here's where people are going to make mistakes. I'm just warning you about this. When I look at this, I have to find d rho. Can everybody see this would be d rho? It's the row component of the D vector, right? Now, multiply that by row. What do you get? 5 over row times row is 5, isn't it, class? What's the derivative of 5 with respect to row? 0. And 0 divided by row is still 0. This term goes away. Can you all follow? Now, next term, what is d phi based on what I put down? I hope you can read it. It's 6 sine of phi, right? What's the derivative of that with respect to phi? It's 6 cosine phi, correct? So this is going to be, down here is going to be 6 cosine of phi plus, go to the last one with respect to z. It's as obvious as it seems. Derivative of 2z with respect to z is 2. That's equal to rho v. If you were asked to figure out where that's 0, how would you do it? At what value of phi it's 0? What would you do? Set it equal to 0, right? Take 2 to the other side, so you have minus 2, correct, class? Then divide by 6. So you have minus 1/3 is cosine of phi. You take the inverse cosine of minus 1/3 to find out where phi is 0, or where it is 0. Do you all follow me, class? This is the class. Yes, sir.
What about the 1 over rho in the equation for the d phi?
I'm sorry. You're absolutely right. I'm being very careless today. I'm sorry. It would be there. My bad. You would have to put that in. I'm sorry about that. But you all follow me on this, class? Now, I want to tell you one other thing about this. The spherical coordinates bother people a lot when you're doing divergence. Don't let it. In his book, he has the form. Now, most of the time, you only get things that vary with r. He has a form that has both. That's the standard type, I think it is. So for his, in spherical coordinates, I'm going to put it right here. Just going to mention that a lot of times, one other thing, I will give you the cylindrical and spherical form of the divergence, or the curl, or the gradient, or the Laplacian. You'll see that in the back of your book, but I won't give you the Cartesian form. Y'all hear me on that? See, Cartesian's the simple one. You have to know that one by heart. Anyway, so when they talk about spherical coordinates, and again, the only thing you're going to do is mathematically execute the derivatives. That's it. So here in spherical coordinates, divergence of d is what? In your book, you'll have it as 1 over r squared d dr, right? And here it's going to be what? R squared, right, times dr? Doesn't he have this form, class? Take a look at his book. Then he's going to have plus what? 1 over, and it's going to be, is it r sine theta in here?
Yeah.
R sine theta. And then he's going to have d theta. Actually, I don't know which one he has first. Yeah, he's got that. And then it's going to be a theta sine theta, right? And then plus, and then he's going to have 1 over, I think this is going to be his 1 over r, this is the phi integration. Yeah, it's 1 over r sine theta phi theta, yeah. And I shouldn't put a there, I should put d actually. But you all follow me? That's a form. Now, I'm about out of time, but if I give you a vector of b, you can get rho v by executing this. Let me just mention one thing that please take note of this. You see how there's an r squared there? Before you do any derivatives, before you do anything, multiply r squared times dr to see what's left. A lot of times it's a constant. And then take the derivative after you do that multiplication. That's important. The only other thing I'll tell you is a lot of times with these, this might be a cosine times a sine, if you have a derivative there, it's gonna be done in two parts. Derivative of the first times the second, plus the second times the derivative of the first. Just keep that in mind. These are things to watch out for when you're doing this. They're not hard, I'll give you problems. I want to tell you, next time we're talking about voltage, okay? I'll give you a bunch of problems. Voltage is real, real important. And you all have had that in circuits, right? I mean, most people have a pretty good understanding of voltage. What is voltage in a nutshell? It's electrical pressure, right? It tells you how much pressure, electrical pressure difference there is between 2 points. And if you let a charge go and it's at a positive electrical potential, there's a negative electrical potential that it can travel to, that's its direction. We'll get there next time. You're going to see the voltage that I talked about. I mean, when I get done with this, I think you'll have an appreciation for how simple a lot of this stuff becomes. But I'll try to make it simple and I'll give you homework, all right? All right.